The Airbus A380 is a super jumbo, the world's biggest passenger airliner. A pioneering marvel of the skies, it's packed with cutting-edge technology. Yet it owes its very existence to the most unlikely breakthroughs and inventions.
Wow! This is just glass!
These engineering connections range from a 19th century rocket to an ancient Mongol bow, and from the soaring genius of an eagle,
Look at that, there you can see it,
to the humble bicycle pump.
What's all that got to do with the high-flying technology of the Airbus A380? We're about to find out.
Airbus 007 clear, takeoff 32 left, 290 degrees 8 knots.
This is the Airbus A380, also known as the Super Jumbo Jet. I'm setting out on a journey to uncover the A380's hidden links to brilliant ideas from across the world and throughout history. I'm about to reveal the engineering connections behind the biggest airliner the world has ever seen.
You can't help but just be stunned by the sheer size of the thing. It is the only aircraft where the passenger seats run the full length of the fuselage from front to back on both the lower and upper decks.
The cabins are 6.5 meters wide
It's the width of it.
and 50 meters long.
It is huge.
The A380 can carry up to 853 passengers, 35% more than its nearest competitor.
It's big. It's very big.
The wings are immense. 70 family cars could park on each one. But if the wings are too long, it can cause problems.
It stands to reason that the world's biggest airliner is going to need the world's biggest wings. And they are absolutely huge. The total wingspan is almost the length of a football pitch. They have to provide enough lift to get 560 tons of people and machinery off the ground. But believe it or not, if these wings were built to a conventional design, they'd need to be even longer, and the A380 wouldn't fit into most of the world's airports. There's no good being able to fly if you've got nowhere to fly to.
There are international restrictions on the maximum size of aircraft to avoid collisions as they taxi around airports. The absolute limit on wingspan is 80 meters. The A380's wings must be short enough to fit regulations, yet they must still create enough lift to get the world's biggest airliner into the air. The Airbus designers found a brilliant solution by drawing inspiration from the animal kingdom. But how did they do it? I'm about to take the first steps in my investigation. Aerospace engineer Dr. Peter Barrington thinks I should get a feel for how a conventional wing creates lift. And the best place to do that is in his wind tunnel at the University of Kingston in London. Peter's given me a handheld smoke generator so I can make the airflow visible.
So, Peter, how does it work and how can this help explain it?
Okay, well, basically the key thing to a wing is the cross-sectional shape. And that bends the air around the wing. The wing is able to make the flow go a lot faster on the top than it goes on the bottom.
The shape of the wing is designed so that air moves faster above than below. As a result, the air above the wing is at lower pressure than normal. So the higher pressure underneath the wing pushes upwards, creating lift for the whole aircraft.
You do get the sense that lift, flight, is just a function of that shape of the wing. That's all it can do.
The same smooth flow of air creates lift all the way along the wing. Or almost all the way. Peter's about to show me that conventional wings have a serious downside.
if you move a bit this way, see what happens as you come a bit closer to the end. A bit closer.
Out to the tip of the wing.
Exactly, yeah.
There it goes.
The airflow at the wing tip looks completely different. Instead of a clean, steady flow, there's a spiraling whirlpool of air. It's called a wingtip vortex. High-pressure air from underneath the wing is leaking around the wing tip and pushing down on the top surface.
That last 5% of the wing isn't really doing anything for you. It's not generating much lift.
The vortex means the wing tip doesn't provide any lift. So the wing is longer than is really necessary. And for the Super Jumbo jet, that's a supersized problem. This A380 prototype was launched through a curtain of illuminated smoke. The test showed that the world's biggest wings would suffer from huge vortices at the wingtips. To compensate for the loss of lift, the A380's wings would have to be made even longer. Too long to fit in with airport size regulations.
The Airbus designers had to find a way to clip their wings down to size. And it's a story that reveals the secret of soaring like a bird.
For the next stage of my investigation, I'm meeting another leading aerodynamics expert. But I hear he can be a bit difficult. His name is Cossack. And he's a steppe eagle, a species named after the wide-open plains of the Central Asian steppe.
I'll be honest, he's a big, impressive-looking thing.
Cossack is a scavenger by nature, and his lifestyle gives him a very similar problem to the A380.
He's gone.
To soar high above the plane in search of food, he needs a thermal, a rising column of warm air around 20 meters wide. But like the A380, his wings can't be too long, otherwise his turning circle will take him outside the thermal. So his wings are perfectly adapted for maximum lift with minimum length. And today he has agreed to take part in an unusual experiment. Oxford University zoologist Graham Taylor is going to show me exactly how Cossack deals with wingtip vortices by filming his wings in flight.
So these are little wireless video cameras.
So you can fit cameras to him.
Right, this is the tricky bit.
What do you do with that?
And I try and put this in his face.
Cossack's handlers help him into the Eagle Cam harness. And now he's ready for his close-up.
Okay.
Wow. With a bit of luck, what we're hoping for is that these cameras are pointing along the wings, aren't they?
That's right.
So we might actually see how they work and what they do. It's fantastic. Right.
It's blowing in the right direction for a good flight.
Yes, yes, yes. There you go, there you go. Yes, yeah, there's a beauty.
Cossack heads for the wide blue yonder, this time broadcasting on Eagle Cam.
There, you can see it. That was right along the wing. Is that what we're looking for?
That's what we're looking for.
Cossack can manipulate the feathers at the tips of his wings. To get maximum lift, he curls them upwards until they're almost vertical. This is the key to getting rid of wingtip vortices for highly efficient flight.
When it's actually soaring around in thermals, what you'll see then is that the wings are taking a heavy load the whole time. And as it does that, those wingtip feathers are curled up the whole way through that it's turning around.
It's disrupting this vortex that rolls around the end of the wing.
That's right.
Cossack's using his tip feathers to create what's called a winglet. This natural adaptation acts as a barrier against the vortex, blocking the path of air as it tries to flow around from underneath his wing. So he doesn't need long wings. His shorter, more efficient wings do the job. The question is, can engineers apply the same trick to these wings? And this 560-ton bird, the Airbus A380. There's a hidden connection between the wings of the world's biggest airliner and the wings of an eagle. In wind tunnel tests, engineer Peter Barrington showed me how airliner wings suffer from spiraling vortices at the wingtips. Now we plan to solve the problem. This modification, inspired by an eagle's wingtip feathers, is called a winglet.
Okay, have a look at the airflow now.
As expected, the main body of the wing has a smooth airflow.
Maybe now we get to the tip.
But here at the wingtip, there used to be a spiraling vortex.
What do you see?
No vortex.
Now it's smooth. The vortex trying to curl around the wingtip finds its path blocked by the winglet.
So it's as simple as that. Basically, it's a barrier that stops the air getting round.
Exactly.
And as a result of that, we win back this stretch of wing.
Indeed.
The vortex has been forced away from the wingtip and up to the top of the winglet. So the entire surface of the original wing is now creating lift, effectively doing the same job as a longer wing.
That's what the eagle was doing.
Indeed. I mean, I think if we had as long as the eagle did to evolve, we could probably get this a little bit smaller.
Winglets can be made almost vertical to keep the total wingspan to an absolute minimum, just like an eagle's wings.
So it turns out eagles are really good at flying.
They are.
Yeah.
Extremely good.
The world's biggest airliner was saved by one of Mother Nature's innovations. But solving one problem creates another. Once the monster is in commercial service, how do you keep its running costs to a minimum? Because in the cutthroat airline business, every kilo counts. Extra weight causes the engines to burn precious extra fuel. So the A380 must be kept on a strict diet. And here on the final assembly line, I've got a unique chance to see its skin and bone.
Wow. We never normally see all this stuff because it's hidden behind carpets and internal walls and chairs and all the other comfy stuff we expect. But now to see the skeleton, the structure of the thing. And I'm struck by, well, I suppose the only other man-made thing this big I'd be in would be a building, and it would have thick stone walls. But here, without all the plastic stuff, you can see. It's got to be so tough. But it looks, I hate to say it, fragile.
Even the A380's outer skin must be as light as possible, especially since it covers a surface area of more than 3,000 square meters. So the challenge for the A380's engineers was to keep its weight to a minimum without making it too fragile. Finding out how they did it will take me centuries back in time, to the brilliant idea that connects the A380 with an ancient but deadly Mongol bow. But first, I've come to this abandoned Air Force base in the east of England to do my own testing of lightweight aerospace materials. Paul Hogg, a materials engineer from the University of London, will be my guide. He's bringing in the heavy artillery, along with some unusual ammunition. Chickens.
Very similar to the sort of test they use for aircraft engines and fan blades, basically.
Is it?
Yeah.
The aerospace industry uses chicken guns to simulate high-speed bird impacts at takeoff. It's a vital test of strength for the aircraft's outer skin. A punctured fuselage can cause the cabin to depressurize, asphyxiating the passengers. Or the bird impact could damage a wing, sending the aircraft out of control.
Any particular, I mean, how do we...
First?
I don't know. How do we select a chicken? That one?
That's the one, that's the one.
It's worth it.
This is going to be very messy, isn't it?
I hadn't thought of that. Yes, it is. The chicken is loaded.
Paul sets the chicken gun to fire at a typical A380 takeoff speed. This will be a 290 km/h collision.
Connect my... That is now live.
But which will survive? The chicken or the aluminium?
5, 4, 3, 2, 1. Well, it was worse for the chicken. I'm amazed.
It's deformed a fair bit, but it's certainly kept itself together very well.
There's a dent, but no catastrophic puncture. But on the world's biggest airliner, saving weight is an absolute necessity. So what if we test thinner aluminium at just 0.9 millimeters thick?
This is to save weight. So if we decided that the heavy stuff we used was too much weight, this is what we got.
That's the sort of thing you do, yeah.
Right up, let's see what happens.
But will it survive?
Whoa! Look at that! Straight through. Ooh. Just remind me, this... We haven't used like baking foil or something here. This is...
That's the real thing.
What's given way? Why has it done that? Why can't it withstand that?
Well, it's really just down to the thickness. It's only got a certain amount of give in it. And when you've got a thinner material, then you're really sort of stretching the limits of what it can do. A big hole. Not a good thing in an aircraft fuselage.
The thinner aluminium is stiff enough to make an aircraft's outer skin, but it isn't strong enough to withstand high-speed impacts. It bends, then tears completely like a sheet of paper. No aircraft could risk such a catastrophe on a flight loaded with passengers. But the Airbus designers found a way to make aluminium thin and at the same time incredibly strong. And that's where the Mongol bow comes in. In the 12th century, the Mongol Emperor Genghis Khan set his sights on world domination, and he planned to destroy his enemies with archery. This is the longbow, an extremely powerful weapon constructed from a single piece of wood. The wood must be strong enough to survive the heavy bending force of a man's body weight. But to conquer the world, Genghis Khan needed a bow that could be fired from horseback by mounted warriors in a highly mobile army. I'm about to find out why that was a problem with traditional bowyer Steve Ralphs.
I can see how the principle, the theory works, because, you know, horse, mobile, weapon, great, but practically, how did it actually work? How could I kill somebody with this, sitting on this?
The first shot is here as you come in from the left-hand side of the horse. So it's 1, 2, 3, up and over, 4.
So let me just try those. So, sorry.
If there's one thing I need, it's a compact weapon.
My arm's twisted now, I can't.
And I can vouch for the fact that the longbow is not it.
So the problem with the longbow for this job is its longness.
So what happens if you try to make a shorter bow with the same power from a single piece of wood?
So I'll give you a short bow.
Thank you.
And some protective equipment.
Right. Yeah, that's not worked at all, has it?
Here's why. When a bow is drawn, the outside stretches so that it's longer than before. But the inside squeezes, making it shorter than before. So the bow has to handle two very different forces at the same time. With a shorter bow, the bending is much greater and the wood just isn't strong enough. So the Mongols came up with a brilliant idea. If there are two different forces, use two different materials.
This is horn, it's buffalo horn, sort of thing they would have used. pieces of this, which is, I mean, it's very tough. It doesn't mind being squashed. It can cope with that very well. And then on the outside of that is a layer of sinew, like this, which is happy being stretched. And in fact, I can break it down a bit and we can...
The sinew comes from tendons in a deer's hind legs, and its fibres are highly elastic. The combined properties of horn and sinew make for one ideal weapon.
You actually bind sinew to this side of the bow, the back of the bow. You place horn plates on the inside of the bow, on the belly. And then you can, in a very short bow, you get the same drawing.
Now, if you did that with just a wooden one like the one I just did,
Well, you saw the results.
yeah. But this, you can draw and it can take a bigger curve. Wow, you can feel it.
With buffalo horn on the inside and sinew on the outside, the bow can handle squeezing and stretching at the same time.
It's like elastic.
Mongol bows were short enough to fire from horseback, but still strong enough to hit targets 300 meters away. The Mongols developed not just a great weapon, but a great concept, the composite. Take two materials with useful properties and put them together to make something far better.
As Genghis Khan might have said, it was easy, once you knew how.
Fast forward to the 21st century. These sections of the A380's outer skin are made from a composite of two materials. Like the buffalo horn in the Mongol bow, lightweight aluminium provides stiffness. But with a heavy impact, it will bend, then rupture completely. It needs a second material, like the sinew in the Mongol bow, to give it added strength. And Paul Hogg has given me an amazing suggestion. Glass.
Well, it broke, obviously, but just tell me, I mean, I knew it would break, but tell me why it broke and how it broke.
Well, basically, it's a brittle material, so it was deformed. Cracks just propagated. Some of them propagated all the way out. You can see the other ones are formed here. End of the story.
An ordinary sheet of glass is very brittle. It looks perfectly clear, but it's actually riddled with microscopic cracks. The sudden impact makes the cracks ripple through the whole sheet. You can't build a plane out of that. But as I'm about to find out, there's a way to make glass strong enough to survive a bomb explosion. The outer skin of the world's biggest airliner, the Airbus A380, must be super light and super strong. So the designers borrowed an idea from the 12th century Mongol bow, combining two different materials to make a composite. In the A380, the first material is lightweight aluminium. But the second material must be incredibly strong to withstand high-speed impacts.
Ooh, look at that.
So materials engineer Paul Hogg is about to show me a very special form of glass.
So I just put that in there, yeah?
Yeah, put it in the flame. Sort of, so move it back towards the point of the flame. Keep rotating it to distribute the heat.
Glass becomes a liquid at around 1500 Celsius.
You'll feel it begin to go soft and a bit sort of floppy.
Let's go and bendy.
Let's go now.
Okay. Wow! Wow! We're still connected! Look at that! We are still connected. You may not be able to see it, but we are still connected by glass. That's...
There we go. There we go.
This is just glass.
It's just glass.
So this is pure, ordinary glass that we've just coiled up again. Why is this doing this?
It's thinner and therefore more flexible, but it hasn't got the defects and cracks on the surface, which is why you can coil it quite nicely without it snapping.
This is a glass fibre, and it's very different to ordinary glass. With no cracks, it's incredibly strong.
It's about 6 to 10 times the strength of steel.
If this was steel wire or something, this
would carry about 6 to 10 times as much weight as the steel wire would.
I'm mesmerised by this stuff.
These glass fibres can be woven like textiles to produce sheets of material. The next stage is to add liquid resin. When it dries, it sticks the fibres together to create glass in its strongest form. fiberglass. Let's see if this window can be smashed.
Hey, hammer. So I'll just hit it. That would have done the glass, wouldn't it?
I think it would have done. Try it again. Don't be shy, give it a good welly.
Glass fibers provide the strength. The individual fibers might break, but the cracks can't spread from one to another.
It's quite surprisingly tough, isn't it?
It is.
And fiberglass is even tougher when combined in a composite with aluminium. It's called glass reinforced aluminium, or GLARE for short. The two materials are sandwiched together in layers. The aluminium provides stiffness, like the buffalo horn in the Mongol bow. Fiberglass is like the sinew in the Mongol bow. It provides the strength that aluminium lacks. So, how will GLARE stand up to the dreaded chicken gun?
It's the glass fibre stopping the cracks growing from one layer of aluminium to the other. That's what we're looking to see.
No pressure here, but it's the same thickness as the aluminium that it went straight through. And we're hoping that it feels something that feels flimsy to me. It's also scarily light.
A short bow made from a single material will bend, then break. The composite bow survives. An aircraft skin made from a single material bends, then ruptures. Can the composite skin withstand the impact?
Okay, I've come down to the business end of our little chicken firing range here because I really want to see what happens when the chicken hits the glare. Does it bend? Does it come back? I want to see how it behaves.
You ready, Richard?
Yeah, I think so.
Okay.
Time.
3, 2, 1.
Oh, well, it's not very nice being that close to a very fast chicken, but it's resisted it. It hasn't gone through.
There's a dent, but the glare survives.
It does work. The two materials working together are better than either alone.
That's fantastic, isn't it?
But could glare even stand up to terrorist attack, like these bomb explosions? In tests, the Federal Aviation Administration placed plastic explosive in a luggage container made of glare. This was the result. A box whose strength comes from glass. For the A380's designers, glare is the perfect combination of high strength and low weight, vital for an airliner this size. Glare forms 470 square meters of the A380's outer skin. It's 25% lighter than aluminium, one reason why the world's biggest airliner has better fuel consumption per passenger than a family car. And thanks to composites, an idea inspired by the Mongol bow, it's tough enough for the rigors of flight, even with a novice pilot.
So Richard, if you want to take control of the airplane now, if you get your hand on the stick ready to take over.
Really?
Yep.
Right.
Go for it. If you put full stick to the right now.
Whoa!
There you go.
Whoa!
That's it. And
It feels as light as a feather.
Are we doing aerobatics in the world's largest airline?
When it's in the air, the A380's enormous size is not a problem. But in the next stage of my investigation, I plan to find out why size is a big issue when the A380 is still on the tarmac. This is Airbus headquarters in Toulouse in southwestern France. A nest for breeding the world's biggest birds.
Whoa! This place is unbelievable. Everything in it is vast.
The final assembly line is nearly half a kilometre long and 50 metres high.
Apparently this building is so enormous that, rumour has it, it can form its own clouds up near the ceiling.
On this scale, human beings seem tiny and insignificant. The fully assembled A380 is by far the longest, widest and tallest airliner in history. The upper exits stand nearly 8 metres off the ground. And that's where the problem comes in. If there's an emergency, the passengers have a long way to go to escape and survive. This is an evacuation test of the A380. To satisfy international regulations, all 853 passengers must evacuate, using only half of the plane's 16 exits. They have just 90 seconds, the estimated survival time in the event of fire. To save their lives, passengers need an escape route fast. They're trapped at the height of a 3-storey building with nowhere to go. As a result, the A380 has the biggest evacuation slides in the world. But regulations require the slides inflate in just 6 seconds, so that the first passengers to arrive at the doors don't block the exits. The only way to do it is to make a surprising connection between a life-saving slide and a device that was designed to kill. To prove it, I'm going to build and test my own model of an evacuation slide. My airbag is 50 metres long. Even so, it would take nearly 8 of these to make the same volume as an A380 slide. So maybe inflating it won't be too difficult.
This is a very big bag, which basically is what an evacuation slide is. And when it comes to inflating a bag as quickly as possible, well, there is an obvious way to do it.
It should be as simple as blowing up party balloons. Attach the bag to a cylinder of compressed gas and inflate for exactly 6 seconds as per regulations.
Right, are we ready? 3, 2, 1.
It is inflating.
5, 6.
The trouble is, it's nowhere near fast enough. After 6 seconds, the bag is still much too soft to take the weight of desperately fleeing passengers. So the A380's designers unleashed their secret weapon: rocket power. I'm using 19th century rockets because the primitive design makes it easy to see the key ingredient: gunpowder. These rockets weren't very accurate in their day, but they did create lots of gas, exactly what we need to fill the bag. All I have to do is make sure the rocket can't move.
And here it is. One rocket fits onto this bed at the back, down this pipe leading to the bag. Obviously the rocket is facing this way because I want the exhaust gases going into the bag, not the actual rocket. So, fix it down. I need a light.
This time, I'm using the rocket gas as a booster and combining it with the compressed gas. But will that be enough to fill the bag in the critical 6 seconds? Nice job on the first half of the bag. Not so good on the second. And for an evacuation slide, anything less than full inflation would cost lives.
Well, the rocket gave us more speed, definitely, but we still didn't fill the bag. We need to get more air in. And to do that, the Airbus designers used one of these.
It's called an aspirator, but it's basically just a funnel. As the funnel gets narrower, the rocket gas moving through it speeds up, causing the pressure to drop. That should create a vacuum effect, sucking in extra air from the surroundings to inflate the slide. But will it be enough to transform a weapon into a lifesaver. It's a stunning success, easily inflating in 6 seconds. 2/3 of the gas filling the bag is fresh air, sucked in by the aspirator. And that's how you rescue people with rocket power.
I mean, it works. Clearly, it works. It might have been pretty useless as a weapon of war, but turns out it can save lives.
With this device, the A380's slides inflate in 4 seconds, 2 whole seconds inside the required time. In the emergency drill, all 853 passengers evacuated in 78 seconds, easily beating the 90-second limit. Thanks to rocket-powered slides, the A380 was officially certified to fly. But the designers hope they'll never be used in a real emergency.
Needless to say, if you're an engineer, it's better to ensure that an emergency never happens in the first place.
On any given flight of the A380, one moment above all is fraught with danger. Touchdown. The earth-shattering collision of wheels and tarmac. The world's biggest airliner weighs 560 tons, almost as much as 200 family cars. But a single piece of life-saving technology must bring all 853 people gently to Earth. I'm about to find out what it is by landing the world's biggest airliner myself at New York's John F. Kennedy Airport.
This is not a normal approach to New York.
I'm with pilot Peter Chandler in the A380's state-of-the-art flight simulator. It rocks and rolls on huge hydraulics, making the effect in the cockpit highly realistic.
It's so convincing. Heart's going.
If you're ready,
Yes.
you probably ought to take control.
Yes, right.
And I'll sort out the configuration of the airplane.
Right.
That's the landing gear going down.
So they're now hanging in the breeze, which, you know, would...
Yeah.
For you
Just
and me,
concentrate on following the green cross. So you need to pull the nose up a bit.
Sorry.
Peter's controlling the engines and the A380's airspeed, giving me less to think about. But I must still use the joystick to keep the plane level and straight before the final approach.
Yeah. You're a bit to the right, actually, so you want to come to the left a bit.
All right. Oh, right.
That's it.
A normal soft landing requires an incredibly slow rate of descent. Just 1 meter per second, slower than walking speed.
Back on the stick a bit.
190. Sink rate. Sink rate.
Oh, what does that mean?
No, that's it.
Retard.
That's it.
Retard. Retard.
Good. Well done. Okay, I have control.
My landing was at double the normal speed, so the simulator gave me a very heavy jolt.
I'm actually bathed in a fine layer of sweat.
In real life, this impact would be easily absorbed by the A380's landing gear. Each set of wheels is cushioned by a giant shock absorber, the crucial technology for bringing passengers safely to Earth. Witness this notorious incident at Hong Kong's Kai Tak Airport in 1993. A Boeing 747 gets caught in a heavy crosswind while approaching the runway. As the jumbo jet twists in the wind, a single set of landing gear sustains the entire impact. But it's strong enough to survive. The A380's landing gear is rated to handle such extreme landings at 4 times the normal descent rate. But the colossal A380 is 40% heavier than a Boeing 747. And here's an amazing fact. The The A380's landing gear is based on the same principle as the device that keeps your bicycle in perfect working order. Engineer Todd Todeschino plans to prove it with a bizarre experiment. This is his stand-in for the A380, a 200-kilogram piano. It's going to drop from a crane and land at 30 kilometers per hour. But Todd thinks he can give it a soft landing using exactly the same principle as the A380's landing gear. It comes from an old-fashioned but brilliant invention. You can make a shock absorber from a bicycle pump. If I make the hole smaller, the air can't get out so easily, and it's squashed or compressed, resisting my arm like that. It isn't pumping anything anymore, but it is absorbing the energy. The A380's massive shock absorbers may look like heavyweight high-tech engineering. But Todd thinks each one is just a cylinder with a piston inside. A giant bicycle pump.
Right, big sheet of plywood.
Yeah.
Okay. Piano sitting on top of the plywood. And that's what we drop from the crane. So we'll put the bicycle pumps underneath the piano. So it'll be like a whole load of sort of fingers of bicycle pumps coming down underneath the whole sort of framework.
So this framework becomes our landing gear, if you like.
Yeah.
This gives us a mounting point.
Yeah.
Okay.
Todd gets on with the basic framework, while I find out what we're up against.
For any experiment to be scientifically rigorous, you've got to have a control. That piano is our control. It's just a piano with no landing gear, and I just thought it'd be good to see what happens when it lands. So here we go. Stand clear. That was not a good landing.
If a fully loaded A380's landing gear ever failed, the consequences would be devastating. It seems incredible that it works on the same principle as a simple everyday device. So, is it really possible to save this piano using bicycle pumps alone? The landing gear of the world's biggest airliner has a similar design to a set of giant bicycle pumps. Engineer Todd Todeschino aims to prove it by using bicycle pumps to build landing gear for a piano. The piano sits on a plywood sheet to keep it upright as it falls. He mounts the pumps onto the plywood so the handles hit the ground first and push in the pistons. And Todd's made a careful calculation of the exact number of pumps he'll need.
100 of them, nice round number.
Nice round number. Loving your science there.
But there is method to the madness.
Fill the fellow up.
The A380's shock absorbers are filled with liquid, not air. So Todd's doing the same. It takes more force to squeeze a liquid out of the pump, so it can absorb a much greater shock.
By squirting the water out of this hole, it transfers the energy. It takes it out of the piano falling.
And it's the energy absorbed in squirting that water out of that hole
Yes.
that will give us our damping, that will
Yes.
slow it down.
It would land and it would go like that.
A trial run gives exactly the sort of gradual shock absorber Todd's looking for. Unfortunately, bicycle pumps aren't designed for water. Soon, all 100 pumps begin springing leaks in the final stages of landing gear construction. And now it's a race against time.
If it looks like we're hurrying, we are. It's dripping. There's 100 little drips coming out, and I'm worried that every drop of water that comes out of the pumps is going to be a drop of that extra cushioning to absorb the energy of the fall. We're just hoping it works.
Todd decides to go for a landing while we still have some water left in the pumps. We have to make the drop as soon as possible and put his theory to the test. This is our recreation of the A380 coming in to land, packed with passengers.
Oh,
One 200-kilogram piano ready to fall at 30 kilometers per hour. 100 bicycle pumps ready to absorb the shock simply by pumping water. Can this landing gear prevent a catastrophic crash landing?
Was this your idea or mine?
Yours.
Thank you. 5, 4, 3, 2, 1, pull!
Result!
I think that worked.
was tough.
I was braced for a disaster, but look!
Watch for the water being forced out in the replay. It still looks like a piano, but does it still sound like a piano?
Go on, give us a tune.
Okay, I don't play the piano, but the piano works. That's the key thing.
100 bicycle pumps were enough to bring a falling piano safely to Earth. When the A380 comes into land, the plane's landing gear absorbs the impact in exactly the same way. But it has just 5 shock absorbers, one for each set of landing gear. Instead of water, they pump oil. It's much thicker, so it can absorb a heavier shock. 560 tons hit the tarmac, and 853 people hardly feel a thing. All thanks to the bicycle pump.
The A380 really is a triumph of high-tech engineering. Every single component has been triple tested to perfection. But for me, it's the ideas behind that technology that make this airliner a modern miracle.
The wings are only possible thanks to a design by Mother Nature. The highly advanced outer skin wouldn't exist without the brilliance of Mongol bowmakers. And it takes a special kind of genius to turn a machine that kills into a machine that saves lives.
Simple, really.